Hello and welcome once again for another ES340 video. This is day 13 part A. So now we are entering chapter 6, which is about entropy. And we'll discuss a bit more entropy from the perspective of a microscopic system later. But for right now, we're still going to focus on the macroscopic picture here. Then we'll get a much more clear picture of what entropy is once we dive into the microscopic perspective. But in any case, we have Clausius's inequality, which, remember, said that for an internally reversible process, we have the following fact. Sorry, this was around the boundary here. Around the boundary is equal to the entropy production, say, in the cycle. Well, negative of the entropy production in the cycle. Now, I'm not gonna derive this. Your book does a nice job of showing why this is the case, but we are going to want to be able to discuss changes in entropy, just like we've discussed now at this point. Remember, up to this point, we've mostly seen the energy balance equation and the energy rate balance equations, right? So we discussed changes in energy and the various different types of ways that they can change, right? The change in internal energy, the change in kinetic energy, the change in potential energy. Also then, of course, heat. Whenever there's heat transfer happening, there's a change in energy. And whenever there's work done, again, there's a change in energy. So that's where that whole equation comes from. So we're also going to be interested now from the second law perspective of changes in entropy. And you can kind of see the relationship, and like I said, the book does a nice job of actually deriving this, but you can see the relationship for the change in entropy. Entropy is given by S, by the way, capital S. And the lowercase would be specific entropy. And that's what you'll actually read off of the tables. So now you should have at this point already seen on the tables this little lowercase s. That's our specific entropy. But the change in entropy is just going for an internally reversible process. It's going to look like this. Okay, so this is going to be our change in entropy, or delta S, in other words. So notice that our, in this case, our change in entropy is intricately related to the heat, right? This is our heat term. So we need heat transfer. And as we'll find, this is a key part of getting, producing entropy is related to heat. Entropy changes are related to heat transfer. So heat transfer is going to be very intricately related to the entropy of a system. And in differential form, on a differential basis, let's call this equation 1. Equation 2, on a differential basis, we can just write it in this way. And I'll make a note about entropy. Again, we're just going to focus for now on it as at the macroscopic perspective, and we'll get a better kind of idea of what entropy is when we start talking about it from the microscopic perspective. So we'll have a brief time where we just discuss that so that we can understand better what entropy is. But entropy is an extensive property. Now, just like before, I just already mentioned that we're going to want to be, because we're going to be dealing with an equation very similar, except for it's going to be the entropy balance equation now rather than the energy balance equation. So I want you to kind of, in your mind, make this association. For the energy balance equation, we're kind of dealing with the first law of thermodynamics, and the entropy balance equation, we're dealing with the second law of thermodynamics. This is kind of just a mapping that you can have in your mind here. So we're going to lead into the entropy balance equation. We're not going to get there yet in this video, but we will get there soon. And the entropy balance is going to require us to go to the tables just like we did for the energy balance. Okay, so we had to go to find the enthalpy for energy rate balance, right? That was a common thing that we had to do. Find the specific volume, find other things to help us to help us in those in dealing with those equations. We're going to need that again. So you already know how to look at the tables. I'm just going to write down a reminder that that we can have we can have like a mixture. And we need to use the quality, say, to determine what the entropy value is in the table. We might also need, just like before, we might also need to refer back to the tables to find to go up and down the table, as you recall. So we might also have to use linear interpolation in that case, right? So this one we have if we have a mixture, we have this equation. If we don't have the value labeled in the tables, not because it's a mixture, but because we're going between rows of the table now or something like that, we could have linear interpolation. So it's just like before. If we are in the condensed, this should all be familiar. Liquid region, we can take S to be approximately equal to SF of the temperature or pressure. Of the temperature, excuse me. We have to use the temperature values there. So we can approximately take S to be equal to the fluid value, the F value on the table when we're in the condensed region. And this is exactly as before. Remember when we were dealing with, say, the TV diagram, right? If we're over here, this is the condensed region. Right on here, this is the saturated liquid. Right, the blue right on the curve there is the saturated liquid. The red is condensed. And for other values, we did exactly the same thing. We said, we said H, the enthalpy in this case is approximately equal to, in the condensed region, right, is approximately equal to H F of T, just like these, just like that we're doing here with the entropy. Okay, so we can have both of these scenarios. And obviously, if you're in the superheated region, which is over here, you have to use the superheated tables, right? So I'm not going to go over and fully review that. We have other videos and stuff to review, but that's the basic idea. Okay, so now the TS diagram. Okay, so we've discussed now, something like on the TV diagram. We also have a TS diagram, which is the temperature entropy diagram, and this is actually going to be the specific enthalpy in this case. And again, we're going to get a very similar curve to what we saw before, except for now we will be interested in the constant enthalpy curves, the constant pressure curves, the constant specific volume curves. We might be interested in those. I'm not going to really cover those too deeply, but you can imagine what you at least can see what those curves kind of look like. And just like before, over on this curve is very similar in the sense that over here we have saturated vapor, right? And then over here we have saturated liquid. And in between we have a mix, right? So as the enthalpy goes in between here, we're gonna have mixed values for a mixture of different types of phases here. So when you get outside, just like before, as I was showing up here, you get into the condensed over on the left here, and over on the right you get into the superheated. So it's very similar. That's why I'm not going to really go into much coverage of this, but it exists, the temperature entropy diagram. And then finally, the Mollier diagram. That's the last thing I'm going to cover in this video, and we'll have another video here, part B of this, to cover the rest of the material here. And the Mollier diagram is enthalpy, right? Our enthalpy versus our specific entropy. So the specific enthalpy versus specific entropy diagram. And this one is interesting in the sense that notice where the critical point falls, for instance. This is very different from what we have before. It falls way down here. So this little tiny region would be down on the curve, would be saturated liquid. Up here in right on the curve again, we're saturated vapor. And as we go further up the curve, all the way over this curve, by the way, we're saturated vapor. And as we go further up the curve, notice the quality here as we're going up. So as we get closer and closer up there, we're in a mixture, obviously, if we're inside here. And the mixture gets higher and gets closer and closer to vapor as we move up this curve now. And finally, again, just like before, outside over here, like we're in the superheated region, right? And that's way down here, down in this region where we'd be in the condensed. So that's maybe a pretty makes it quite different from the other diagrams that we've seen before, is that the critical point has moved to a very different place. That's all that I have for this video. Hope to see you again soon.